Imagine the sky is on fire. It's 12,800 years ago and you're standing somewhere in North America. Maybe near what will one day be Michigan, or perhaps the grasslands that will become the Carolinas. The sun has just set and you're settling in for the night when suddenly the darkness explodes into light. Streaks of brilliant white tear across the sky. Not one, not two, dozens of them. They scream overhead with a sound like nothing you've ever heard, a roar that shakes the ground beneath your feet. Then the impacts begin, massive explosions that turn night into day. The horizon erupts in flames. Heat washes over you from miles away. The air itself seems to be burning. Within hours, fires are raging across the continent. Animals are fleeing in panic. The sky has turned black with smoke and ash. And this isn't just happening here. It's happening across North America, across Europe, across Asia. The entire northern hemisphere is burning. This is the Younger Dryas impact hypothesis, and it's one of the most controversial ideas in modern science. See, something catastrophic happened to Earth 12,800 years ago. That's not up for debate. The evidence is crystal clear. The planet suddenly plunged into a deep freeze that lasted over 1,000 years. Temperatures dropped by 15 degrees Fahrenheit in less than a decade. Glaciers that had been retreating started advancing again. And across the Americas, dozens of species of massive animals, mammoths, mastodons, saber-toothed cats, giant ground sloths, all went extinct within a geological eye blink. What caused it? That's where things get interesting. If you're listening to this while falling asleep, perfect. That's exactly what these are for. And hey, drop a comment telling me where you are and what time it is there. I love seeing Berlin at breakfast, Sydney at sunset, Chicago at midnight, all watching the same story unfold. It's wild. For decades, the mainstream explanation has been straightforward. Natural climate cycles. The Earth was coming out of the last ice age, temperatures were fluctuating wildly, and these changes triggered the cold snap and extinctions. Nothing cosmic, nothing catastrophic, just the planet doing what planets do. But then some scientists started noticing things that didn't fit. Strange materials in soil layers from exactly 12,800 years ago. Tiny spheres of melted rock. Nanodiamonds that only form under extreme pressure and heat. Carbon deposits that look like they came from massive wildfires. Platinum anomalies. And they found this stuff everywhere, scattered across multiple continents in a thin layer that dates to the exact moment the climate went haywire. Their conclusion? A comet or asteroid exploded over North America, possibly fragmenting into multiple airbursts across the hemisphere. The impacts triggered continent-wide firestorms, threw enough dust and debris into the atmosphere to block out the sun, and kicked off the climate catastrophe we call the Younger Dryas. It's an incredible claim, the kind that rewrites textbooks if it's true, and that's exactly why it's been so controversial. Other scientists have spent years challenging the evidence, questioning the methods, proposing alternative explanations. The debate has been fierce, sometimes brutal, and it's still raging today. Here's what makes this story so fascinating. Both sides have compelling evidence. Both sides have legitimate experts making carefully reasoned arguments. This isn't pseudoscience versus real science. It's real scientists looking at the same period in Earth's history and reaching radically different conclusions. So what really happened 12,800 years ago? Did the sky actually fall? Or are we seeing patterns in the data that aren't really there, trying to find a dramatic explanation for events that have simpler causes? That's what we're here to explore. Not to tell you what to believe, but to walk through the evidence, examine the arguments, and maybe understand why this particular mystery has scientists so divided. Because whatever happened at the end of the Ice Age, it changed the world forever, and understanding it might tell us something crucial about our own fragile moment in history. Let's start at the beginning, with the climate catastrophe that started it all. Picture this. You're living 12,900 years ago. Your ancestors have survived the last ice age, watched glaciers retreat for thousands of years, seen forests return to landscapes that had been frozen tundra for millennia. The world is warming. Life is getting easier. Animal herds are expanding. Plants are flourishing. Your people are thriving in ways that would have been impossible just a few thousand years earlier. Then suddenly everything changes. Not gradually, not over centuries. Within a single human lifetime, maybe even within a decade or two, the world plunges back into Ice Age conditions. Temperatures in some regions drop by 15 degrees Celsius, that's 27 degrees Fahrenheit, in less than 20 years. Glaciers that had been retreating for millennia stop, then surge forward again. Forests die back. Grasslands turn to tundra. Rivers freeze solid. Animal populations that have been expanding crash. And your people, who have been spreading across continents, colonizing new territories, developing increasingly complex societies, suddenly find themselves fighting for survival again. This wasn't a myth. This wasn't speculation. This happened. We know it happened because the evidence is written in ice cores from Greenland, in sediment layers from lake beds across the northern hemisphere, in fossilized pollen from ancient bogs, in the growth rings of trees that were alive when it occurred. This event has a name, the Younger Dryas, and it remains one of the most dramatic and mysterious climate events in recent Earth history. The Younger Dryas lasted from approximately 12,800 years ago to 11,700 years ago. That's roughly 1,100 years of renewed Ice Age conditions, dropped right in the middle of a warming trend that had been ongoing for thousands of years. Scientists named it after a small Arctic flower called Dryas octopetala, which suddenly reappears in the geological record across Europe during this period. The plants returned to regions where it hadn't grown for thousands of years, told researchers something dramatic had happened to the climate. But here's what makes the Younger Dryas so puzzling. It wasn't just cold, it was abrupt. Climate scientists talk about the event in terms that sound almost catastrophic. The temperature changes happened faster than almost any natural climate shift we know of in the entire geological record. Ice core data from Greenland shows temperature drops happening so rapidly that you could see the change within a single decade. Some researchers suggest the initial cooling happened in as little as 3 years. 3 years. Think about that. Imagine the world you know today suddenly transforming into an Ice Age environment before your next presidential election. That's the kind of speed we're talking about. The impacts were global, but varied dramatically by region. The Northern Hemisphere got hit hardest. Greenland and Northern Europe saw the most extreme temperature drops. Glaciers that had been melting for thousands of years suddenly advanced again. The Scandinavian ice sheet, which had retreated hundreds of miles, surged back across landscapes that had been ice-free for generations. North America experienced similar devastation. The Great Lakes region, which had been warming steadily, plunged back into deep freeze. Spruce forests that had been migrating northward died back and were replaced by tundra vegetation. Mountain glaciers in the Rockies, which had been disappearing, suddenly grew again. But the effects weren't limited to the far north. Climate reconstruction suggests that tropical regions experienced significant changes too, though less extreme. Rainfall patterns shifted. Monsoons weakened. Some regions that had been relatively wet became arid. Others saw the opposite. The Atlantic Ocean circulation system, which governs weather patterns across much of the Northern Hemisphere, seems to have been disrupted. Some scientists think the Gulf Stream, that massive current that carries warm water from the tropics to northern Europe, may have weakened or even temporarily shut down. Without that warm water, regions that had enjoyed relatively mild climates suddenly faced brutal winters. Sea levels, which had been rising as glaciers melted, either stopped rising or may have even dropped slightly as water got locked back up in expanding ice sheets. Coastlines that had been flooding as the Ice Age ended suddenly stabilized, and then, roughly 1,100 years after it started, the Younger Dryas ended. Just as abruptly as it had begun. Temperature records from Greenland ice cores show warming rates that are even more dramatic than the initial cooling. Within perhaps 50 years, maybe less, global temperatures shot back up. Glaciers retreated rapidly. Forests exploded northward. Within a few generations, the world had transformed again. By 11,700 years ago, the planet had entered the Holocene, the current geological epoch. The climate stabilized at roughly modern temperatures. The Ice Age was finally, definitively over. And human civilizations, which had been struggling through the Younger Dryas cold snap, suddenly found themselves in a world perfect for agriculture, permanent settlements, and everything that would follow. But that 1,000-year interruption changed everything. For scientists, the Younger Dryas raises profound questions. Climate doesn't usually work this way. Natural climate changes, even dramatic ones, typically happen gradually over centuries or millennia. Orbital variations, solar output changes, volcanic activity. These are the normal drivers of climate shifts, and they operate on timescales that give ecosystems time to adapt. The Younger Dryas was different. It was too fast, too dramatic, too precisely timed. It looked less like a natural climate fluctuation, and more like something had hit the Earth's climate system with a hammer. For decades, the leading explanation involved ocean currents. The idea was that as the North American ice sheet melted, massive amounts of fresh water flooded into the North Atlantic. This fresh water was less dense than salt water, so it didn't sink like normal ocean water does. The result was a disruption of the Atlantic circulation system, the same system that drives the Gulf Stream. Shut down that circulation, and you shut down the heat transport that keeps northern Europe and the North Atlantic relatively warm. This explanation made sense. It fit the evidence reasonably well. It explained why the cooling was most extreme in the regions around the North Atlantic. Most scientists accepted it, but it had problems. The timing wasn't quite right. The geography was a bit off. Some regions showed climate changes that didn't fit the ocean circulation model, and most troublingly, the sheer speed of the temperature changes seemed too fast even for a circulation shutdown. Something else might have happened. Something more dramatic. Something that came from outside the Earth's climate system entirely. Something, perhaps, that fell from the sky. Picture the world 13,000 years ago. North America wasn't just home to deer and bears and the animals we know today. It was a landscape dominated by creatures that would seem almost mythical if we hadn't found their bones scattered across the continent. Woolly mammoths standing 13 feet tall at the shoulder, their massive curved tusks gleaming in the sun, herds of them stretching across the grasslands like living mountains, giant ground sloths, some as large as modern elephants, moving slowly through forests with claws the size of machetes. Saber-toothed cats, their iconic fangs extending 7 inches past their jaw, perfectly designed for piercing the thick hides of Ice Age megafauna. Dire wolves, 25% larger than modern grey wolves, hunting in packs capable of taking down prey that would terrify any predator today. American mastodons browsing in spruce forests, giant short-faced bears, the largest mammalian land predator ever to exist in North America, standing 12 feet tall on their hind legs. Glyptodons, armored mammals the size of Volkswagen Beetles, their club-tailed bodies covered in thick bony plates. Giant beavers, weighing up to 220 pounds, building dams that would dwarf anything modern beavers construct. Horses. Yes, horses originated in North America. Multiple species of them, from small pony-sized animals to creatures as large as modern draft horses. Camels too, which evolved here before migrating to Asia and South America. Giant peccaries, enormous ground-dwelling birds, armadillo-like creatures the size of small cars. This wasn't just a handful of impressive species. This was an entire ecosystem of giants, a megafauna paradise that had existed for millions of years, and then, in what amounts to a geological eye blink, most of them vanished. The timing is what makes paleontologists lose sleep at night. Between roughly 13,000 and 11,000 years ago, North America lost 72% of its large mammal genera. Not species, genera, entire groups of related animals. South America lost 83%. Australia had already lost most of its megafauna by this time, but the Americas were experiencing mass extinction on a scale that rivaled the asteroid impact that killed the dinosaurs, at least in terms of large animal diversity. Now here's where it gets tricky. When exactly did each species go extinct? You'd think this would be straightforward. Find the most recent fossil, radiocarbon date it, and there's your answer. But it's not that simple, not even close. First problem, preservation bias. Large animals don't fossilize easily. They need to die in exactly the right conditions, get buried quickly, avoid scavengers, and then somehow survive thousands of years without being destroyed by erosion or geological processes. Most individuals that die leave no trace at all. So the last fossil we've found is almost certainly not the last individual that lived. Second problem, the radiocarbon dating method itself. Carbon-14 dating works beautifully for material between about 500 and 40,000 years old. But right at the edge of the Younger Dryas, you're working at the limits of the technique's precision. A date of 12,800 years might actually be anywhere from 12,600 to 13,000 years. That 400-year margin of error becomes crucial when you're trying to determine if extinctions happened suddenly or gradually. Third problem, contamination. Bones sitting in the ground for 13,000 years can absorb carbon from groundwater, from plant roots growing through them, from microbes colonizing their porous surfaces. Each source of contamination can make the bone appear younger than it actually is. So a mammoth that died 13,000 years ago might radiocarbon date to only 11,000 years because of contamination, throwing off your entire extinction timeline. Despite these challenges, the pattern that emerges is striking. The vast majority of reliably dated megafauna extinctions cluster right at the beginning of the Younger Dryas, around 12,800 years ago. Not all of them, and there's definitely some variation by region and species, but the concentration is impossible to ignore. Mammoths appear to have survived in isolated populations for thousands of years after the main extinction pulse. A small population hung on at Wrangel Island in the Arctic Ocean until about 4,000 years ago. That's more recent than the construction of the Egyptian pyramids. But the vast continental herds, the populations that had dominated North American landscapes for hundreds of thousands of years, they disappeared right at the Younger Dryas boundary. The same pattern shows up with mastodons, giant ground sloths, horses, camels, and most other megafauna. Continental populations collapsing around 12,800 years ago, with possible remnant populations surviving in refuges for varying periods afterward. But here's what's really puzzling. Not everything went extinct. Bison survived. Elk survived. Moose, caribou, musk oxen all made it through whatever catastrophe killed their larger neighbours. Modern deer populations thrived. Bears adapted and continued. Wolves got smaller but survived. So what was different about the animals that died versus the ones that lived? Size seems to be a factor. The larger you were, the more likely you went extinct. But it wasn't just about being big. American bison are massive animals and they survived. Musk oxen are substantial, and they're still around. So size alone doesn't explain the pattern. Some researchers think it's about reproductive strategy. Animals that had long gestation periods, produced few offspring, and took years to reach sexual maturity were more vulnerable than animals that reproduced quickly. Mammoths took 22 months to produce a single calf, and that calf needed years of care before independence. Bison have much shorter gestation and faster maturity. When populations get hit hard, fast reproducers can bounce back. Slow reproducers spiral toward extinction. Others point to dietary specialization. Mammoths and mastodons were highly adapted to specific plant communities. When the Younger Dryas disrupted those ecosystems, specialists suffered more than generalists. Deer can eat almost anything. Mammoths needed specific grasses and sedges that suddenly became scarce. The ecological consequences of losing all this megafauna were catastrophic and long-lasting. These weren't just big, impressive animals. They were keystone species that shaped entire ecosystems. Mammoths and mastodons acted like living bulldozers, knocking down trees, creating grasslands, dispersing seeds across vast distances. When they disappeared, forests expanded into areas that had been open grassland for millennia. Giant ground sloths dispersed seeds for plants that had evolved specifically to be eaten by giant animals. When the sloths vanished, some of those plants went extinct too, or became restricted to tiny relic populations. The ripple effects cascaded through food webs. Predators that had specialized in hunting megafauna suddenly lost their prey base. Scavengers that had relied on megafauna carcasses to get them through lean times faced starvation. Plant communities reorganized. Fire regimes changed without large herbivores to keep vegetation trimmed. The entire character of American ecosystems transformed, and it all happened in remarkable synchrony with the Younger Dryas climate disruption. Coincidence? Maybe. But the timing is awfully suggestive. Something happened 12,800 years ago that fundamentally altered the trajectory of life on this planet. The question is, what? For decades, scientists have been puzzling over the Younger Dryas. They had mapped its timeline, documented the temperature drops, traced the extinctions, but they couldn't agree on what caused it. The ice sheet collapse theory had problems. The orbital forcing models didn't quite work. The volcanic eruption hypothesis left too many questions unanswered. Then, in 2007, something unexpected happened. A team of researchers led by Richard Firestone, Alan West, and Simon Warwick Smith published a paper that would ignite one of the most intense scientific debates of the 21st century. They proposed something that sounded like science fiction. What if the Younger Dryas wasn't caused by gradual climate processes or slowly accumulating ice sheets? What if it was caused by something that happened in a single day, maybe even a single hour? What if 12,800 years ago a fragment of a comet slammed into Earth's atmosphere above North America and triggered the entire catastrophe? This was the Younger Dryas impact hypothesis, and it was bold, controversial, and backed by what its proponents claimed was physical evidence found at dozens of sites across multiple continents. The hypothesis went like this. Around 12,800 years ago, Earth encountered debris from a fragmented comet, not a single massive asteroid like the one that killed the dinosaurs, but a swarm of objects, some perhaps miles across, others smaller, all screaming into the atmosphere at tens of thousands of miles per hour. The researchers proposed that these fragments exploded in the atmosphere over North America. Multiple airbursts, like the Tunguska event in 1908, but vastly larger and happening simultaneously across a continent-sized area. The immediate effects would have been catastrophic. Each airburst would have released energy equivalent to multiple nuclear weapons. The shock waves would have flattened forests across thousands of square miles. The heat would have been intense enough to ignite wildfires on a continental scale. But the real devastation came next. Those airbursts would have thrown enormous amounts of debris into the upper atmosphere. Not just dust and ash, but vaporized rock, melted minerals, exotic materials created by the extreme pressures and temperatures of the impacts. This debris cloud would have circled the globe within days, blocking sunlight, dropping temperatures, turning summer into winter across the entire northern hemisphere. The wildfires would have raged for weeks or months, consuming the forests that had flourished during the warm Alarud period. The smoke would have added to the atmospheric debris, creating a kind of impact winter that lasted for years. And the megafauna, those ice age giants that had survived hundreds of thousands of years of climate fluctuations, they would have been caught completely unprepared. Mammoths and mastodons, dependent on massive amounts of vegetation, would have starved as the plants died. Giant ground sloths that needed specific types of forest would have lost their habitat overnight. Predators like saber-toothed cats and dire wolves would have followed their prey into extinction. The Clovis people, those sophisticated hunter-gatherers who had spread across North America, would have faced similar devastation, not just from the initial impacts, though those would have been horrific for anyone living near the airburst zones, but from the collapse of the entire ecosystem they depended on. Within a generation, their distinctive tool tradition vanished from the archaeological record. The hypothesis explained everything. The sudden temperature drop, the extinction wave, the disappearance of Clovis culture, the beginning of the Younger Dryas cold period. One cosmic collision accounting for all the mysteries that had puzzled scientists for decades. But extraordinary claims require extraordinary evidence, and this is where the hypothesis gets really interesting. Because Firestone, West, and their colleagues claimed they had found that evidence. At archaeological sites across North America, at the exact layer corresponding to 12,800 years ago, they reported finding materials that shouldn't be there under normal circumstances. First, there were nanodiamonds. These are microscopic diamond crystals that form only under extreme pressure and temperature. You find them at known impact sites like the Chicxulub crater in Mexico. You find them in meteorites, but you don't normally find them in random sediment layers. The team reported finding nanodiamonds at dozens of sites across North America, all at the same stratigraphic level, all dated to the start of the Younger Dryas. Then there were magnetic spherules, tiny balls of iron and other metals with distinctive magnetic properties. These form when materials are flash heated to extreme temperatures, melted, and then rapidly cooled. You see them at impact sites, in volcanic deposits, but also potentially in airburst debris fields. The researchers found these spherules at site after site, always in the same layer, always associated with the Younger Dryas boundary. There was a distinctive carbon-rich layer at many sites. Not ordinary charcoal from normal wildfires, but dense black matte containing exotic forms of carbon, including fullerenes and carbon spherules. This layer suggested massive simultaneous wildfires burning across an enormous area, exactly what you'd expect from multiple airbursts igniting forests across an entire continent. They found platinum and other rare elements concentrated in this boundary layer. Platinum is rare in Earth's crust, but common in certain types of asteroids and comets. Finding it concentrated at the Younger Dryas boundary suggested extraterrestrial material had been deposited. There were microscopic melt glass fragments, created when sand or rock is heated so rapidly that it melts and then cools into glass. This happens at nuclear test sites, at impact craters, anywhere extreme heat meets silicate materials. The research team catalogued these materials at site after site: Murray Springs in Arizona, Blackwater Draw, New Mexico, Topper in South Carolina, sites in Mexico, Venezuela, Syria, Belgium. The geographic spread was enormous, suggesting an event with continental or even global effects. Most compellingly, all of this evidence appeared in a layer that could be dated with remarkable precision. Using radiocarbon dating, pollen analysis, and stratigraphic correlation, researchers could show that this boundary layer dated to 12,800 years ago, give or take a few decades, exactly when the Younger Dryas began. The hypothesis gained attention incredibly quickly. Popular science media loved it. A cosmic catastrophe wiping out megafauna and ancient civilizations made for compelling headlines. Documentary filmmakers jumped on it. Suddenly the Younger Dryas wasn't just another climate transition, it was cosmic drama, catastrophe from space, the kind of event that could happen again tomorrow. But the scientific community was more cautious, because if this hypothesis was true, it would overturn decades of careful work on climate transitions, extinction mechanisms, and archaeological interpretation. It would mean that catastrophism, the old idea that Earth's history is shaped by sudden disasters rather than gradual processes, might be more important than anyone had thought. The debate that followed would become one of the most contentious in recent scientific history, because the evidence wasn't as clear-cut as those initial headlines suggested, and the implications were enormous, not just for understanding the past, but for thinking about the future. If a cosmic impact could trigger a climate catastrophe and mass extinction just 12,800 years ago, what might happen if it occurred today? So, if something really did hit Earth 12,800 years ago, where's the evidence? This is where the story gets fascinating, because we're not talking about one smoking gun. We're talking about dozens of subtle clues scattered across multiple continents, each one potentially pointing to an extraterrestrial impact, or potentially not. That's the maddening beauty of this mystery. Let's start with the most dramatic piece of evidence, the black mat. If you dig down to the right depth at hundreds of sites across North America, you find this distinctive dark layer. Sometimes it's just a few centimeters thick, sometimes thicker. It's rich in carbon, loaded with charcoal particles, and it sits precisely at the Younger Dryas boundary, exactly where you'd expect to find evidence of whatever triggered the climate catastrophe. The black mat has been known to geologists for decades. That's not controversial. What's controversial is what it represents. Impact hypothesis supporters say this is the signature of massive wildfires, continental-scale burning triggered by airbursts or impacts. Imagine fragments of a comet or asteroid exploding in the atmosphere across North America, creating firestorms that consumed millions of square kilometers of forest and grassland. The charcoal layer is what's left, the cremated remains of an entire ecosystem. But here's where it gets tricky. Not everyone agrees on the interpretation. Critics point out that charcoal layers aren't uncommon in the geological record. Wildfires happened throughout prehistory. Lightning strikes, volcanic activity, even human campfires could create localized burning. Finding charcoal at a particular time period doesn't necessarily mean cosmic catastrophe. It might just mean fire, and fire is everywhere in Earth's history. So the impact hypothesis proponents needed more evidence, something that couldn't be explained by ordinary terrestrial processes. Enter the nanodiamonds. Nanodiamonds are exactly what they sound like. Microscopic diamond crystals so small you need an electron microscope to see them. They form under conditions of extreme temperature and pressure, the kind of conditions you get during meteorite impacts or nuclear explosions. When researchers started looking carefully at sediments from the Younger Dryas boundary, they found nanodiamonds, lots of them. At sites across North America, Europe, and even the Middle East, this was huge, because nanodiamonds don't just appear randomly in nature. You need either extreme volcanic activity, which there's no evidence for at this time, or you need an impact. The distribution pattern was even more suggestive. Higher concentrations in North America, diminishing as you moved away. Exactly what you'd expect if something hit or exploded over the North American ice sheet. But, and this is a big but, other researchers had trouble replicating these findings. Some laboratories found nanodiamonds at the boundary layer, others didn't. Some found them at the boundary, but also found them in layers above and below, which would suggest they're not unique to the Younger Dryas event. The debate got technical fast, with arguments about contamination, measurement techniques, and what actually counts as a nanodiamond versus other carbon structures that might look similar under certain viewing conditions. Then there were the magnetic spherules. These are tiny spherical particles, rich in iron and other metals, with compositions suggesting they formed at high temperatures. When cosmic material hits Earth's atmosphere at hypersonic speeds, it melts. The molten droplets solidify into these little spheres as they fall. They're like frozen raindrops, except the rain is vaporized asteroid material. Researchers found these spherules in Younger Dryas boundary sediments at multiple sites. The exciting part was their composition. Some contained exotic metals and crystalline structures consistent with extraterrestrial material. Some showed signs of having been heated to temperatures exceeding 2,200 degrees Celsius, far hotter than any natural terrestrial fire. This looked like solid physical evidence of cosmic material hitting Earth. But again, the critics had questions. Magnetic spherules can form from other processes. Cosmic dust constantly rains down on Earth, adding about 40,000 tons of extraterrestrial material every year. That's been happening for billions of years. So, finding some spherules with cosmic signatures doesn't necessarily prove an impact event. You'd need to show an unusual concentration, a spike in the amount of cosmic material arriving all at once, and that's harder to demonstrate conclusively. The search expanded to other markers. Iridium, a rare element on Earth's surface but common in asteroids, showed elevated levels at some Younger Dryas boundary sites. Not as dramatically elevated as at the Cretaceous-Tertiary boundary that marks the dinosaur extinction, but elevated nonetheless. Platinum group elements, also rare terrestrially but common in cosmic materials, appeared in anomalous concentrations at certain locations. Each piece of evidence seemed suggestive, but none was definitive, and that's the central problem with this entire hypothesis. We're looking for the fingerprints of an event that happened 12,800 years ago. Any impact or airburst over the ice sheet would have left most of its evidence locked in ice that melted thousands of years ago. What we're finding are the peripheral traces, the scattered debris, the secondary effects. The geographic distribution of these proposed impact markers is telling, though. The highest concentrations appear in a band across North America, stretching from the Atlantic coast to the Pacific. Secondary evidence shows up in Europe, particularly in sediments from lakes that would have been catching atmospheric fallout. There are hints of similar markers in South America and even in Syria, where one site showed a distinctive layer of melt glass, the kind that forms when sand is subjected to extreme heat. This distribution pattern suggests something dramatic happened, something that affected a huge area simultaneously. But it doesn't definitively prove impact. Critics argue that many of these markers could be explained by the massive glacial lake outburst floods we know occurred around this time. Torrential floods carrying exotic sediments from far away, concentrating particles that normally would be spread out, creating the illusion of a spike in cosmic material when it's really just normal background levels getting concentrated by hydraulic sorting. The challenge in distinguishing extraterrestrial from terrestrial particles is immense. Take those magnetic spherules. Yes, some formed at high temperatures, but couldn't they have formed during wildfires? Forest fires can create localized temperatures hot enough to melt some materials. Couldn't volcanic activity, even from distant sources, explain some of the chemical anomalies? Earth's geological processes are complex and interconnected. Proving that a particular microscopic particle came from space, rather than from some unusual but terrestrial process, is incredibly difficult. More recent work has focused on platinum. Several studies have found significant platinum spikes at the Younger Dryas boundary, not just in North America but globally. Platinum is extremely rare in Earth's crust, but common in certain types of asteroids. A global platinum spike is harder to explain away with terrestrial processes, but even here there are complications. Some scientists argue that volcanic activity can concentrate platinum under certain conditions. Others point out that changes in ocean chemistry during climate shifts can cause platinum to precipitate out of seawater, creating apparent spikes that are really just chemical reorganization. The physical evidence, then, is suggestive but not conclusive. It's tantalizing. There's something there, multiple independent lines of evidence all pointing to the same narrow time window. But whether that something is cosmic impact, or some combination of terrestrial processes that just happen to coincide with the Younger Dryas boundary, that's still being fought over in academic journals and conference halls. The search for cosmic fingerprints continues, with new techniques, better instruments, and more careful analysis being applied every year. What seemed clear a decade ago gets muddied by new data. What seemed impossible gets reconsidered in light of better evidence. This is science at its most uncertain and its most exciting. But here's where the story gets complicated, because for every researcher convinced they found evidence of a cosmic impact, there's another scientist looking at the same data and seeing something completely different. The skeptics aren't killjoys trying to ruin an exciting story. They're doing what science demands, questioning, testing, trying to poke holes in the hypothesis until either it falls apart or becomes stronger. And when it comes to the Younger Dryas impact hypothesis, they've found a lot of holes to poke. The first major problem is reproducibility. This is fundamental to science. If you claim you found nanodiamonds in a sediment layer, other researchers should be able to go to similar sites, collect similar samples, and find the same thing. But that's not what happened with the Younger Dryas boundary layer. When Firestone's team first published their findings in 2007, they reported nanodiamonds at sites across North America. Tiny industrial diamonds that could only form under extreme heat and pressure, the kind you'd expect from a cosmic impact. Other researchers immediately started looking for the same thing at other Younger Dryas sites. Some found nanodiamonds, many didn't. Even more problematic, some researchers went back to the exact same locations where Firestone's team had collected samples and couldn't replicate the findings. This is a huge red flag in science. If your evidence only shows up sometimes, if it depends on who's looking and how they're looking, that suggests the evidence might not be what you think it is. Maybe the nanodiamonds aren't really there. Maybe they're there, but they're not actually diamonds. Maybe they're there and they are diamonds, but they didn't come from an impact. In 2011, a team of researchers led by Nicholas Pinter published a comprehensive review of the impact hypothesis. They visited 29 sites across North America that supposedly showed impact evidence. At most sites, they found nothing unusual in the Younger Dryas boundary layer. No nanodiamonds, no magnetic spherules, no iridium spikes, nothing that couldn't be explained by normal geological processes. Where they did find unusual materials, they often had mundane explanations. Those magnetic spherules that looked like they'd been melted in a cosmic fireball. Many turned out to be magnetite particles that naturally form in soils. Some were probably from wildfires, which can reach temperatures high enough to create small magnetic particles. Others might have been contamination from modern sources, farm equipment, construction, even the metal tools used to collect the samples. The nanodiamonds were even more problematic. Some researchers argued that what Firestone's team identified as impact diamonds were actually just misidentified mineral structures. Certain types of carbon and silicate minerals can look very similar to nanodiamonds under some analytical techniques. If you're expecting to find diamonds and you're using methods that can't always distinguish diamonds from similar materials, you might see diamonds where none exist. This is called confirmation bias, and it is one of science's most dangerous enemies. When you really want to find something, you're more likely to interpret ambiguous evidence as supporting your hypothesis. The only defense is rigorous methodology and independent verification, and that's exactly where the impact hypothesis was failing. Then there's the crater problem. This one is fundamental. If a comet or asteroid hit North America hard enough to trigger a global climate catastrophe, where's the hole? We found impact craters from events millions of years ago. The Chicxulub crater that marks the asteroid that killed the dinosaurs is 66 million years old and still perfectly visible. Yet we can't find a crater from just 12,800 years ago. Impact proponents have tried several explanations. Maybe the object exploded in the air before hitting the ground. Airbursts can deliver enormous energy without creating a crater. The 1908 Tunguska event in Siberia flattened 800 square miles of forest, but left no crater because the object exploded several miles up. But Tunguska was a tiny event compared to what would be needed to trigger the Younger Dryas. To cause global climate change, you'd need something much larger, and objects that large don't just vaporize in the atmosphere, they make craters, big ones. Maybe the crater is hidden under the ice sheets. The Laurentide ice sheet covered most of Canada during the Younger Dryas. Perhaps the impact hit there, and the evidence is buried under thousands of feet of ice, or was scoured away when the ice melted. Possible, but unlikely. Ice sheets preserve evidence remarkably well. If there was a massive crater under Greenland or northern Canada, modern ice-penetrating radar should be able to detect it. Researchers have looked. They haven't found anything. Maybe it wasn't one large object, but multiple smaller fragments. This could explain why there's no single large crater. The fragments could have scattered across a wide area, creating multiple smaller impacts or airbursts. Again, possible. But where's the evidence? Multiple impacts should leave multiple craters, or at least clear geological signatures of multiple high-energy events occurring simultaneously. We don't see that either. Some skeptics go further, questioning whether the platinum anomaly even requires an impact. Platinum is rare in Earth's crust, but it's also not impossible to find in higher concentrations under certain conditions. Volcanic eruptions can bring up platinum from deeper in the Earth. Certain types of erosion can concentrate platinum in sediment layers. Even some types of bacteria can accumulate platinum from their environment. Without clear impact markers like shocked quartz, tektites, or a crater, finding slightly elevated platinum levels doesn't necessarily mean anything cosmic happened. It might just mean something unusual, but entirely terrestrial occurred. The extinction timing creates another serious problem. When you look closely at the dates, many of the North American megafauna extinctions don't actually line up with the Younger Dryas boundary. Some species disappeared thousands of years before, others hung on for thousands of years after. If a cosmic impact killed them all, you'd expect to see a sharp extinction horizon, everything dying at once, right at the boundary layer. But that's not what the fossil record shows. Mammoths, for instance, survived on isolated islands until just 4,000 years ago. If a continent-wide catastrophe killed their mainland relatives 12,800 years ago, how did island populations survive? The more likely explanation is that mammoths were already declining due to climate change and human hunting, and different populations disappeared at different times as local conditions varied. Even the Clovis culture decline might not need a cosmic explanation. Archaeological evidence shows that Clovis technology didn't actually disappear. It evolved into other tool traditions as people adapted to changing environments and the loss of megafauna to hunt. This is normal cultural evolution, not evidence of catastrophe. The peer review process has been particularly harsh on the impact hypothesis. Multiple papers claiming evidence for the impact have been challenged or retracted after other scientists couldn't replicate the findings. This doesn't mean the researchers were being dishonest. Science is hard. Analyzing microscopic particles in ancient sediments is incredibly difficult. Mistakes happen. But the pattern of non-replication suggests systematic problems with the methodology. By 2012, the scientific consensus had largely turned against the hypothesis. Most geologists, archaeologists, and climate scientists considered it interesting but unsupported by solid evidence. Not disproven entirely, you can't prove a negative, but sufficiently weak that it didn't deserve serious consideration alongside established explanations for the Younger Dryas. But science doesn't end with consensus, and that's when things got interesting again. Before you imagine a comet tearing across the sky, lighting up the northern hemisphere like a cosmic blowtorch, you have to meet the quieter suspects, the slow workers, the forces that shape ice ages without any help from space at all. Because long before anyone proposed an impact at the start of the Younger Dryas, climate scientists already had a story built not on fire from the sky, but on water, on wind, on the way Earth's own systems can suddenly turn against themselves. In the traditional explanation, the Younger Dryas wasn't a freak accident. It was a relapse. A cold snap in a planet that was already wobbling its way out of the last ice age. Things had been warming for thousands of years. Glaciers were retreating, sea levels were rising, forests were creeping north into zones that had been frozen tundra. Then, for reasons that seemed almost mundane at first, the system tripped. To understand how, picture the North Atlantic not as a patch of ocean, but as the beating heart of the planet's climate. Warm, salty water flows north from the tropics like a conveyor belt. As it reaches higher latitudes, it cools, becomes denser, and sinks. That sinking drives a deep global circulation loop that moves heat around the world. Shut that down, and you don't just cool one region, you reorganize the whole climate system. This is the core of the North Atlantic freshwater hypothesis. During the deglaciation, North America was capped by a staggering mass of ice, the Laurentide ice sheet. Imagine a continent wearing a frozen helmet 2 kilometers thick. As the planet warmed, that ice didn't just melt politely into nearby rivers. It broke, it carved, it collapsed in pulses. Huge glacial lakes formed along its edges. One in particular, often called Lake Agassiz, covered an area larger than all the modern Great Lakes combined. In the freshwater hypothesis, something dramatic happened to those lakes. At some point, an ice dam failed. Maybe it was undermined by meltwater. Maybe it fractured during a warm spell. Maybe it just reached a breaking point. However it happened, the result would have been catastrophic flooding. Billions of tons of fresh water rushing north into the Arctic or east into the North Atlantic in a geological instant. Now think about what that does to the ocean conveyor belt. The sinking of water in the North Atlantic depends on that water being salty and dense. Dump enough fresh water on top and you dilute the salt, lighten the surface layer and weaken the sinking. In some models you can shut it down almost completely. When that happens, heat that used to be carried north stays in the tropics. The North Atlantic and surrounding continents cool rapidly. Sea ice expands, storm tracks shift. Within a few decades, or even a few years, a region can go from relatively mild to brutally cold. To many researchers, that's the Younger Dryas in a nutshell. No comet, no explosion. Just a natural system pushed past a tipping point by its own melting ice. It's an elegant story, but it isn't the only one. Zoom out further, beyond oceans and ice sheets, and you reach an even deeper driver of climate. The geometry of Earth's orbit itself. Over tens of thousands of years, our planet doesn't travel around the sun in a perfectly stable way. Its orbit stretches and relaxes, its tilt wobbles, its axis traces a slow circle in space. These changes, known as Milankovitch cycles, gently alter how sunlight is distributed across the globe. Not the total amount, but the where and when. Sometimes northern summers get a little more sunlight, sometimes a little less. Over long periods, those differences control whether ice sheets grow or shrink. They set the stage for ice ages and for the warm periods in between. By the time of the Younger Dryas, orbital forcing had already nudged the system into a warming phase. That's why the ice sheets were retreating in the first place. The planet was supposed to be coming out of the deep freeze, but orbital cycles are slow. They explain the long rise and fall of ice ages, the broad outline of climate history, not the razor-sharp edge of a 1,200-year cold snap that begins almost overnight. They're like the background music, important, always there, but not the sudden crash of a cymbal that makes you jump. Some researchers have looked instead to the sun itself. Solar variability is another quiet suspect. The sun doesn't shine with perfectly constant strength. It pulses in cycles of about 11 years, waxing and waning in activity, changing the amount of high-energy radiation that reaches Earth. Over longer stretches, it may go through extended lulls or bursts, like the Maunder minimum associated with the so-called Little Ice Age just a few centuries ago. These variations can influence climate by tweaking the upper atmosphere, altering ozone, and subtly shifting wind patterns. In a system already near a tipping point, that kind of nudge might be enough to start a cascade. A few unusually quiet decades from the sun, combined with vulnerable ice sheets and sensitive ocean circulation, could potentially trigger something like the Younger Dryas. But again, the problem is scale. Solar forcing is relatively small compared to the massive reorganization of ocean and atmosphere we see at the onset of the Younger Dryas. It may have been a contributing whisper. It doesn't easily account for the full roar. Then there is fire from below, not from above. Volcanoes are one of the most dramatic natural climate forces we can observe directly. When a major volcano erupts explosively, it can inject sulfur-rich aerosols high into the stratosphere. Those particles reflect sunlight back into space, temporarily cooling the surface. After the eruption of Mount Pinatubo in 1991, global temperatures dipped noticeably for a couple of years. Now imagine not one Pinatubo, but a cluster of large eruptions, or a single truly massive one. Some researchers have asked whether volcanic activity around 12,900 years ago could have kicked off the Younger Dryas. A veil of volcanic aerosols might have cooled the northern hemisphere enough to expand sea ice, alter atmospheric circulation, and push the system into a new equilibrium. The challenge is the timescale again. Volcanic aerosols usually fall out of the atmosphere within a few years. Their cooling effect is sharp but brief. To sustain a 1,200-year cold interval, you'd need either repeated eruptions timed just right, or a sequence of feedbacks, like growing sea ice and shifting currents, that keep the system locked in a cold mode long after the initial volcanic trigger is gone. So on one side you have these natural mechanisms, orbital forcing slowly loading the dice, ice sheets melting, forming glacial lakes poised to burst, ocean circulation waiting at a threshold, the sun flickering slightly, volcanoes occasionally throwing blankets of dust into the high atmosphere. On the other side you have the cosmic hypothesis, a single, spectacular event, an impact or airburst, releasing more energy in seconds than all the world's nuclear weapons combined. Melting ice, starting wildfires, lofting dust and soot into the sky, perhaps even destabilizing those very ice dams that the freshwater hypothesis depends on. Both approaches are trying to solve the same puzzle. How do you take a planet that's slowly warming out of an ice age and snap it back into near glacial conditions in what looks, in the geological record, like a heartbeat? The freshwater hypothesis explains the regional cooling of the North Atlantic and surrounding continents especially well. It fits with our understanding of ocean physics. It has modern analogues in smaller, shorter-lived events. Orbital forcing explains the background state, the fact that there was ice to melt in the first place, and that the world eventually warmed again. Solar and volcanic forcing offer additional nudges and potential triggers. The impact hypothesis aims to unify many of these into one dramatic cause. One event that could, in theory, generate fires, dust, meltwater pulses, and rapid climate reorganization all at once. Standing back, you can see the outlines of two different styles of explanation. One is incremental, many natural levers, each moving a little, combining to tip the system. The other is catastrophic, a single extraordinary blow from space turning the dials all at once. For now, the natural mechanisms remain the baseline, the default story most researchers work from. They're grounded in processes we can model, observe, and test. The cosmic mechanism is more speculative, more controversial, but also more dramatic. To understand what really happened at the dawn of the Younger Dryas, we have to keep both possibilities in mind. The slow forces of Earth, always at work, and the rare, violent visitors from beyond. In the next section, we'll ask an even sharper question. Whatever triggered the cold, was it truly responsible for the great dying that followed? Now drift forward in time to the very end of the Ice Age. The glaciers are pulling back, forests are creeping north, grasslands are shifting like slow green tides across continents, and walking through this changing world are some of the most extraordinary animals that have ever lived. Giant ground sloths as tall as a house, mammoths and mastodons roaming in vast herds, saber-toothed cats stalking the edges of the herds, patient, lethal shadows, enormous beavers, towering camels, armored glyptodons like living tanks. For millions of years, these megafauna had survived cold snaps, warm spells, advancing ice and retreating ice. They were not fragile newcomers. They were veterans of climate chaos. And then they were gone. From Alaska to Patagonia, from northern Europe to Siberia, from Australia to the islands of the Pacific, the same pattern appears in the fossil record. Around the time of the Younger Dryas and the final collapse of the Ice Age, something happens to big animals. Their bones thin out, then vanish. Whole ecosystems that had been stable for tens of thousands of years unravel in what looks, on geological timescales, like an instant. But how instant? And why? This is the extinction question at the heart of the Younger Dryas story. Was it a single catastrophic event? A night when the sky fell and rewrote the rules of life on Earth? Or was it something slower, more complicated, a long squeeze of climate and humans and chance ending in silence? If you look at the fossil dates, you can tell two different stories depending on how you squint. One story says the extinctions were sudden. In places like North America, many megafauna species cluster around the end of the Pleistocene, disappearing within just a few thousand years. On a human scale, that's a long time. On an Ice Age scale, it's a blink. To a paleontologist, a species that lasts 3 million years and vanishes in 5,000 has died in a sudden crash. But another story emerges when you zoom in further. Some species fade earlier, some hang on later. In a few pockets, like certain Alaskan islands, dwarf mammoths survive for thousands of years after their mainland relatives vanish. In parts of South America, large animals persist well into the Holocene. The pattern isn't a clean cliff. It's a ragged, uneven shoreline with little bays and headlands of survival and loss. So was it a single, global event, or a patchwork of local endings spread across continents and millennia? To answer that, we have to bring humans into the picture. By the time the last Ice Age was drawing to a close, our species had become astonishingly good at surviving. We hunted in coordinated groups, we made specialized weapons, we shared knowledge about migration routes, breeding grounds, and animal behavior. We'd been forged by earlier climate crises, and now we walked into new lands with skills no other predator had ever possessed. The overkill hypothesis says this was enough to doom the megafauna all by itself. The idea is brutally simple. Imagine a continent full of animals who have never seen a human. They know about wolves and big cats and packs of dogs, but they have no concept of a small, upright primate that throws spears from a distance, that can track for days, that kills not for immediate hunger, but to store food, to trade, to share. Every time humans move into a new region in the late Pleistocene, something interesting happens. In Australia, large animals start declining not long after human arrival, tens of thousands of years before the Younger Dryas. In the Americas, humans appear, and within a few thousand years, most of the biggest mammals are gone. On islands from Madagascar to New Zealand, the same pattern repeats. People arrive, big animals fade. Supporters of overkill argue that you don't need a comet or some mysterious cosmic trigger. You just need a clever, cooperative, very hungry ape that reproduces faster than elephants and mammoths, and that can hunt year after year, generation after generation. But even this story isn't simple. If humans alone caused the extinctions, why didn't megafauna vanish earlier in Africa and parts of Eurasia, where our species evolved and lived alongside large animals for hundreds of thousands of years? Why do some species, in some places, seem to linger long after people arrive? This is where climate walks back onto the stage. At the end of the last ice age, the world was not changing gently. Temperatures were swinging up and down, ice sheets were melting, and then, during the Younger Dryas, advancing again. Rainfall patterns shifted dramatically. Grasslands turned to forests, then back to grasslands. Lakes appeared, expanded, dried up. For animals evolved for one particular ice age niche, these shifts could be deadly. Climate change alone can drive extinction cascades. You don't have to kill every individual to end a species. You just have to break its life cycle, melt the ice too fast, and the open steppe that mammoths love shrinks away, replaced by dense forests that favor deer and boar instead. Change the timing of plant growth, and the seasonal migrations of herbivores fall out of sync with the food they need. Shrink the range where a species can live, and small, isolated populations become vulnerable to disease, inbreeding, and bad luck. Once the web starts to stretch, it can snap quickly, lose a key grazing animal, and the plants it once kept in check overgrow, changing fire regimes, altering soils, reshaping habitats. Predators that depended on that grazer decline, scavengers lose carcasses, smaller animals either adapt or vanish. An ecosystem is like a net. Cut enough strands and the rest sags and tears. There are places on Earth where we see strong signs that climate played the dominant role. In some high-latitude regions, megafauna decline starts before clear evidence of dense human populations. In others, plant communities reconfigure dramatically right around the time big animals disappear, hinting that environmental stress came first. But there's another possibility, one many researchers now find compelling. Maybe it wasn't humans, or climate, or a possible impact. Maybe it was all of them working together. Picture a mammoth population already stressed by shrinking habitat, thinner winters, and unpredictable food. Calves are a little weaker, adults a little leaner, birth rates a little lower. Alone, this might not wipe them out. They might adapt, shift their ranges, hang on in refuges. Now add humans. Hunters don't have to kill every mammoth. They just have to target the easiest animals, the young, the old, the injured. In a robust population, that pressure might be manageable. But in a climate-stressed population, those extra deaths can push the species past a tipping point. Fewer calves survive, fewer females reach breeding age, and recovery becomes impossible. In this view, climate change sets the stage, weakening the giants. Humans deliver the final precise blows, one hunting season at a time. If there was an impact event around the Younger Dryas, that could have been yet another layer of stress. Fires, dust, regional cooling, disruption of plant communities. Not a single death sentence, but an extra weight on an already overloaded system. The fossil and archaeological records suggest that this synergy of causes didn't play out the same way everywhere. In some regions, like parts of North America, the timing of human arrival, climate volatility, and megafaunal collapse line up so tightly that it's hard to separate them. In others, like mainland Africa, many large animals survived to the present, possibly because they had co-evolved with human hunters over a much longer timescale, learning, quite literally, to fear us. There are also puzzling regional exceptions, isolated islands where big animals persist long after mainland populations vanish, sheltered valleys where certain species linger in the record while their neighbours disappear, places where overkill seems too strong a word, and places where it might be an understatement. So when we ask, was it multiple causes or a single event, the most honest answer may be, it depends on where you were standing and which animal you were. For a mammoth herd in the open plains of North America, the end might have felt abrupt, a few bad decades layered on top of an already challenging century. For a ground sloth in South America, it might have been a slower tightening of the noose, habitat shrinking step by step, hunters appearing more often along the trails. For small animals, rodents and birds and insects, life may have gone on almost unchanged, the age of giants ending above their heads. From our vantage point, looking back through scattered bones and stone tools, it's tempting to search for one clean cause, one simple story, a comet in the sky, a clever hunter, a shifting climate graph. But the past rarely gives us that kind of simplicity. What the extinction question really shows us is how interconnected everything was at the end of the Ice Age. Climate, humans, landscapes, animals, perhaps even cosmic events, all woven together into a single fragile tapestry. Pull on one thread, and the others move, and somewhere in that weave, our ancestors were not just witnesses but participants. In the next section, we'll step closer to them. We'll walk into their camps, look at their tools, and ask a quieter, more intimate question. If catastrophe did come during the Younger Dryas, did humans see it with their own eyes? If an impact really did shake the planet at the start of the Younger Dryas, it didn't happen in a vacuum. There were people here to see it. Not many compared to today, but scattered across the Americas, across Europe, across the Near East, small bands of hunter-gatherers were already living through a world in transition. Glaciers were melting, coastlines were shifting, animals were on the move. And then, according to the impact hypothesis, the sky itself joined the chaos. Archaeology is our way of asking them what happened. The record from this period is patchy and uneven, like an old manuscript with whole pages torn out. But what we do have is tantalizing. Layers of stone tools, animal bones, hearths and campsites, frozen in time at the exact moment the climate lurched back toward Ice Age conditions. In some places, the story seems to continue almost smoothly. In others, something breaks. Nowhere is that break more famous than in the story of the Clovis people. Clovis culture appears in North America around 13,200 years ago, give or take. For a long time, archaeologists thought they were the first humans on the continent. We now know people were here earlier, but Clovis still marks a remarkable moment. A distinctive toolkit spreading over enormous distances in a surprisingly short time. Their calling card is the Clovis point. Long, elegant spear tips with a channel flaked out of the base, designed to fit into a wooden shaft. These weren't crude survival tools. They were precision hunting weapons standardized across thousands of kilometers. From the Great Plains to the American Southeast, from the Rockies to the East Coast, you can find the same basic design, over and over again. Then, very suddenly, Clovis points become rare. In many regions, the layers that contain classic Clovis tools sit directly beneath a dark, charcoal-rich band in the soil. Above that band, Clovis disappears, and new tool types take their place. Different shapes, different strategies, different ways of living on the land. Impact proponents look at that and see a signature, a flourishing culture, heavily invested in big game hunting, thriving at the end of the last glacial period, and then, at roughly the same time the climate snaps back to colder conditions, their hallmark technology fades out. They argue that an impact or airburst event could have set off continent-scale wildfires, devastated megafauna herds, and shattered the ecological niche that Clovis hunters relied on. In their view, what follows is not smooth cultural evolution, it's a scramble. New point types, new hunting targets, new routes across the landscape as herds vanish and plant communities reorganize. They see Clovis not just as a culture, but as a before picture, and the archaeological layer above, full of varied post-Clovis traditions, as humanity's after. But the story's more complicated. Other archaeologists point out that Clovis doesn't vanish everywhere at once. In some areas, there are hints of continuity, of people gradually modifying their tools in ways that look more like adaptation than extinction. They note that hunter-gatherer technologies change all the time, sometimes rapidly, without any need for a cosmic disaster. A new stone source, a new prey animal, a new social alliance can all leave their mark in flint and bone. And then there's the question of timing. Not every site lines up perfectly with the proposed impact date. Some Clovis-like tools seem to persist a bit later. Some post-Clovis technologies may overlap. The archaeological record, viewed closely, is rarely as clean as a single sharp line. Still, standing in a dig pit while the wind blows dust across a layer of ancient charcoal, it's hard not to feel the drama. Under your feet, a world of mammoths, giant bison, and hunters carrying long-fluted spear points. Above your feet, a cooler, harsher world, with smaller animals, different tools, and people learning to live in ecosystems that had just been turned upside down by climate, by human hunting, by something else, or by all of it together. And the Clovis story is only one part of the Younger Dryas puzzle. Across the Near East, at sites like Abu Huraira in modern Syria, archaeologists have documented a different kind of transition. Here, communities of foragers were beginning to experiment with wild grains at the end of the Ice Age. They gathered, processed, and perhaps even tended stands of cereals. Then, right as the Younger Dryas begins, the archaeological layers show signs of shock. Charred plant remains, abrupt shifts in building styles, changes in the types of grains and animals exploited. Some impact researchers claim there are microscopic impact markers, melted glassy particles, tiny spherules, embedded in these layers. If that's true, they argue, it might mean people in the Fertile Crescent literally lived through an airburst powerful enough to shower their village with molten debris. Others caution that these supposed impact markers could have more ordinary explanations. Local fires, human burning of fields, even modern contamination. They agree that the people of Abu Huraira faced a sudden climate downturn. But they don't see proof that the sky had to fall to make that happen. Beyond individual sites, you can step back and look at broader patterns. Human migration routes bend and twist around the Younger Dryas. In Europe, some regions seem to thin out, with fewer sites or smaller occupation areas, suggesting people pulled back to refugees with more reliable resources. In the Americas, settlement patterns shift, with evidence of groups exploring new territories, following different rivers, climbing into new valleys. Did they move because of an impact? Because of the rapid return of cold, dry conditions as the North Atlantic circulation faltered? Because their favourite animals were disappearing? Archaeology rarely gives clean answers. It gives hints. It shows you that something changed. that human footprints suddenly appear in new places, that old camps go quiet and new ones light up, but it can't tell you what the sky looked like or what stories people whispered around the fire at night. For that, some researchers turn to something more fragile than stone and bone: memory. All around the world, traditional societies preserve myths about fire from the sky, serpents of flame, stars that fall and burn the earth, floods unleashed after a great celestial battle. In Australia, in North America, in Eurasia, there are stories where comets, blazing objects, or angry gods in the heavens reshape the world in a single terrible moment. A few scholars have wondered whether some of these myths could be very old enough perhaps to echo real encounters with comets or meteor airbursts. They imagine a band of hunters watching a streak of incandescent light cross the sky, hearing a distant boom, feeling a hot wind sweep over the plain. The experience lodges in their minds, passed down, embroidered, transformed, but never entirely forgotten. Could any of these stories preserve a faint memory of Younger Dryas events? We don't know. Oral traditions can be astonishingly durable, but also fluid. Myths absorb later experiences, borrow motifs from neighbours, evolve with each retelling. A tale of fire from the sky might recall a meteor, a volcanic eruption, or nothing more than a dramatic sunset combined with human imagination. Correlating specific myths with specific ancient events is a tempting game, but a dangerous one. It's easy to see patterns where none exist. And that is the central challenge of the archaeological dimension. We're trying to line up three different clocks: the geological clock, measured in cores and isotopes; the archaeological clock, measured in radiocarbon dates and stratigraphy; and the human clock, measured in stories, traditions, and the rise and fall of cultures. Each clock has its own uncertainties, its own smudged numbers and missing gears. Radiocarbon dates have error bars. Sediment layers can be mixed and disturbed. Oral traditions can stretch and compress time in ways that make no sense to a modern calendar. When proponents of the Younger Dryas impact hypothesis point to Clovis disruption, charred village remains, sudden shifts in settlement patterns, and worldwide myths of skyfire, they see convergence. Multiple lines of evidence, they argue, are all pointing in the same direction. People witnessed something extraordinary. Skeptics counter that human societies are always living through extraordinary things. Volcanic eruptions, droughts, floods, epidemics, social conflicts all leave similar fingerprints. They warn that if you go looking for catastrophe in the archaeological record, you will always find enough ambiguity to support the story you want to tell. So we're left in a liminal space. We can say that human communities live through the Younger Dryas, that their tools, diets and movements changed in ways that reflect a world suddenly made colder and less predictable. We can say that some of these changes were abrupt, others gradual. We can even say that somewhere, sometime, people probably did stand under a sky lit by a disintegrating comet or a flaming meteor. What we can't yet say, with the certainty of a courtroom verdict, is that a single cosmic impact reshaped human history at 12,800 years ago. The evidence whispers, but it doesn't shout, at least not yet. And as we listen to those whispers from stone points and buried hearths, from migration routes and mythic tales, we have to keep balancing curiosity with caution, because the next layer of evidence, the next excavation, the next improved date could shift the story again. In the meantime, the archaeological record offers something almost as powerful as certainty, a glimpse of resilience. Whatever happened at the start of the Younger Dryas, people endured it. They adapted, moved, reinvented their lives. They carried their memories of cold, of hunger, of strange lights in the sky forward into new landscapes and new ages, and their descendants, thousands of years later, would begin to ask what exactly they had lived through. So where does all of this leave us? After decades of arguments, papers, conferences, and more than a few academic shouting matches, what do scientists actually think about the Younger Dryas impact hypothesis today? To answer that, we need to slow down a little. Picture the scientific community not as a single voice, but as one of those scattered Ice Age bands from earlier in our story. Small groups, working in different places, sharing information through conferences and journals instead of trade routes and campfire stories. Some are climate modelers staring at computer screens filled with swirling colours. Some are geologists picking through layers of mud and ice. Some are impact specialists who spend their lives looking for craters and cosmic shrapnel. All of them are trying to reconstruct what happened 12,800 years ago from evidence that's been buried, eroded, or melted for millennia. If you asked most climate scientists and quaternary geologists today whether the Younger Dryas was caused by a cosmic collision, many would quietly shake their heads. The current mainstream view is cautious, even skeptical. Abrupt climate shifts, they point out, can happen without help from the sky. Changes in ocean circulation, especially the Atlantic overturning system, can flip like a switch. Meltwater from retreating ice sheets can pour into the North Atlantic, freshening the surface, disrupting deep water formation, and suddenly plunging the Northern Hemisphere back into near-glacial conditions. You don't need an incoming comet for that. Just ice, gravity, and a planet still recovering from the last glacial maximum. Impact specialists tend to be even more reserved. They know what a confirmed impact looks like. Craters with shatter cones in the bedrock, melt glass with unmistakable high-pressure minerals, a clear global layer rich in extraterrestrial elements like iridium, or in shocked quartz grains aligned in specific ways. These are the smoking guns that nailed the dinosaur-killing Chicxulub impact. For the Younger Dryas, no such definitive crater has been universally accepted, and the alleged geochemical signals are patchy, inconsistent, or contested. From their perspective, the case isn't closed, it's just not proven. But that's only part of the landscape, because not everyone agrees. There is still a persistent, serious minority of researchers who think something extraordinary happened at the Younger Dryas boundary, something that might involve a fragmented comet or a swarm of meteors exploding in the atmosphere. They point to layers of tiny glassy spherules found at multiple sites, to nanodiamonds, to peaks in platinum and iridium, to charcoal and soot spikes that might signal massive wildfires. They argue that when you line up all these clues, scattered across North America, Europe, even the Middle East, it starts to look less like coincidence and more like a pattern. And the pattern hasn't stayed frozen. Over the last decade, the impact hypothesis has evolved. Early versions spoke confidently, maybe too confidently, about a single giant explosion that wiped out mammoths, Clovis hunters, and triggered the Younger Dryas all at once. That bold, simple story drew attention. It also drew heavy fire. Critics tore into the data. Some labs couldn't reproduce the findings. Some claim the supposed nanodiamonds were misidentified minerals. Others argued that the glassy spherules could be produced by normal Earth processes. Volcanism, lightning strikes, wildfires, no comet needed. Comet. Under that pressure, the hypothesis changed. It became more cautious, more fragmented. Some proponents now talk about a series of smaller airbursts rather than one cataclysmic strike. Some separate the questions. Maybe there really was an unusual impact event, but maybe it only contributed to, rather than fully caused, the climate shift. Maybe it helped stress megafauna that were already vulnerable. Maybe it scarred human populations that were already under pressure from environmental change. The sharp edges of the original claim have been worn down, smoothed by years of critique and counter-argument. While the ideas have shifted, the tools have changed too. Scientists today have technologies that would have seemed like sorcery to the first people who dug mammoth bones out of riverbanks and wondered what killed them. Ultra-high-resolution radiocarbon dating can now pin down the timing of events within decades, sometimes even finer. That matters, because to link an impact to a climate shift or an extinction, they have to line up in time almost perfectly. If the black layer with strange particles appears centuries before or after the climate flips, the story falls apart. Geochemists use mass spectrometers to measure trace elements in ancient sediments at parts per trillion levels, detecting tiny whiffs of cosmic chemistry buried in mud. Electron microscopes scan grains of glass and metal so small you could fit thousands on the head of a pin, looking for the telltale textures of hypervelocity impacts. Ice cores from Greenland and Antarctica, sliced into razor-thin layers, preserve annual snapshots of atmospheric dust, ash, and even platinum peaks that might indicate something unusual falling from above. Remote sensing has joined the hunt. Satellite-based radar and gravity mapping can peer beneath ice and sediment, searching for hidden craters that might date to the right time. That's how researchers identified structures like Hiawatha in northwest Greenland, a buried crater-like formation under the ice sheet. When it was announced, some wondered if this was finally the missing Younger Dryas crater. But as dating techniques improved, the likely age began to drift older, probably too old to match the event. Intriguing, but not the smoking gun. Computers help in other ways. Climate modelers can now simulate what would happen if a large airburst or multiple impacts injected dust, soot, or water vapor into the atmosphere at high latitudes. Would it be enough to disturb ocean circulation? Could continent-scale wildfires really blanket the northern hemisphere sky with smoke for years? The simulations don't give simple yes or no answers, but they help narrow what's physically plausible and what would require miracle-level coincidences. Despite all this, the Younger Dryas remains stubbornly resistant to final judgment. That's partly because the farther back you go in time, the thinner and more ambiguous the evidence becomes. Sediments are disturbed, ice layers deform, rivers cut away crucial deposits. Glaciers scrape the landscape clean. Imagine trying to reconstruct a crime scene after 12,800 years of rain, wind, and tectonic shuffling. Some clues survive, but many are gone forever. The ones that remain are often smudged, broken, or out of place. There are also genuine scientific tensions built into the problem. Different lines of evidence don't always agree. Some sites show clear platinum peaks right at the Younger Dryas boundary. Others don't. Some labs find nanodiamonds. Others, using different preparation methods, don't see them at all. Some climate records show abrupt changes almost overnight. Others record a more gradual transition spread over decades or centuries. It's like listening to a choir where not everyone is singing quite the same melody. And yet, for all the disagreement, there are things almost everyone accepts. The Younger Dryas was abrupt. It was global, or at least hemispheric. It was tightly tied to changes in ice sheets and ocean circulation. Massive ecological shifts and extinctions happened in its orbit, even if the exact cause and effect chains are still tangled. Human cultures living through it had to adapt rapidly or disappear. Within that shared framework, the debate continues. On one side are those who say, we have enough known natural mechanisms, ice sheets, meltwater pulses, ocean currents, to explain the Younger Dryas without invoking an impact. Extraordinary claims, they argue, require extraordinary evidence, and so far the impact hypothesis hasn't cleared that bar. On the other side are those who reply, the Earth is hit by comets and asteroids all the time on geological scales. We know airbursts like Tunguska in 1908 can flatten forests. We know impact proxies cluster at the Younger Dryas boundary at many sites. We know megafauna and some human cultures vanished in a narrow window. Maybe, they say, we're missing something because we expect the past to look like the few impacts we have already recognized, and this one was different. fragmented, airborne, partly melted into ice. Between these positions lies a wide zone of uncertainty, where cautious curiosity lives. That's where most of the current scientific landscape actually sits, not in absolute rejection, not in confident belief, but in a kind of disciplined agnosticism. The impact hypothesis is not the consensus explanation, but it isn't entirely dead either. It exists in a liminal space, intriguing, contested, periodically revived by new data, repeatedly challenged by new critiques, and so the work goes on. New cores are drilled from lake beds and peat bogs. New techniques are applied to old samples. New craters are searched for beneath ice and ocean. Each discovery adds another piece to the puzzle, even if it sometimes raises more questions than it answers. For now, the Younger Dryas impact hypothesis remains what so much of deep history is, a story balanced on the edge between what we know and what we can only infer. Not a solved mystery, not a discarded myth, but an open case file on the desk of a very patient planet. So why does any of this matter? Why spend so much time arguing about a cold snap that happened more than 12,000 years ago, about mammoths and mastodons and a maybe impact that no one alive will ever see? Because the Younger Dryas is more than a mystery story. It's a stress test, a natural experiment that shows what happens when the climate system, the biosphere and human societies get hit, hard and fast, by something they didn't see coming. Think about the timescales. For most of Earth's history, climate has drifted slowly. Ice sheets grow over tens of thousands of years. Forests advance and retreat step by step, century by century. Species adapt, migrate, or die out, but usually with time to try. The Younger Dryas wasn't like that. In some records, temperatures in parts of the northern hemisphere plunge by as much as 10 degrees Celsius in just a few decades. In a human lifetime, the world changes from warming to near glacial. Rivers freeze longer, rain patterns flip, grasslands turn back into tundra. If you're a megafauna species, that's brutal. If you're a small band of hunter-gatherers depending on those animals, it's terrifying. Modern climate change is different in its causes. We're driving it, not an impactor or a freshwater pulse, but the core lesson is similar. Earth's climate can move fast, faster than forest can shift, faster than big animals can evolve, faster than human cultures are comfortable adapting. The Younger Dryas is like a warning preserved in ice and mud layers saying, this system you live in, the one that feels stable and predictable, it can jump. And when it jumps, everything tied to it jumps too. For climate scientists, the Younger Dryas is a calibration point, a real-world case study of abrupt change. If you want to understand tipping points in ocean circulation, in ice sheets, in atmospheric patterns, you look at episodes like this. You ask, what started it? How big was the trigger compared to the response? How did the system recover? Did it snap back quickly, or did it creep out over centuries? If the impact hypothesis is right, or even partly right, it adds another layer. It says, sometimes the climate doesn't just drift into a new state. Sometimes it gets shoved. A sudden injection of dust, soot and aerosols into the atmosphere. Vast areas of burning biomass. Shock waves that shatter ice, disturb oceans, disrupt circulation. A single night or a single year that pushes a delicate system across a threshold. But even if the impact story turns out to be wrong, the lesson doesn't vanish. The Younger Dryas still happened. It still shows us that Earth's climate is not only sensitive to gradual changes like rising CO2, it's also capable of sharp, non-linear shifts when certain parts of the system, like North Atlantic circulation, are disturbed. For extinction risk assessment, that matters. Because from an extinction's point of view, the cause of the shock isn't the main issue. What matters is speed, magnitude, and how many different stressors hit at once. During the Younger Dryas, Large animals in many regions were already under pressure. Habitat changing, human hunting intensifying, resources becoming patchy. Then the climate flips. Growing seasons shrink. Snow persists. Water sources freeze or move. For a megafaunal population already living close to the edge, that extra push may be the difference between struggling and collapsing. Today, we're doing something eerily parallel. We're fragmenting habitats, over-harvesting species, spreading invasive organisms and diseases, and then on top of all that, we're ramping up global temperatures at a rate that, in some metrics, rivals the fastest shift in the geological record. The Younger Dryas suggests that ecosystems don't fail gracefully. They don't always fade away slowly, giving us plenty of warning. Sometimes they hit thresholds, and then things cascade. Plant communities reorganize suddenly. Predator-prey relationships break down. Migration routes stop working. You see regional extinctions, then continental ones, not in a smooth curve, but in surges. From a planetary defense perspective, the Younger Dryas debate opens a different door, whether or not this particular cold snap was triggered by objects from space. We know for certain that impacts have shaped Earth's history. The dinosaurs didn't vanish gently. They were removed violently by a rock from the sky roughly 10 kilometers across. Smaller objects hit more often. Some explode in the atmosphere, some hit oceans, some slam into land and vanish beneath erosion and plate tectonics. The Younger Dryas impact hypothesis is, in a way, asking, what does the world look like after a medium-sized cosmic punch? Not a dinosaur killer, but still big enough to start fires, send tsunamis racing across coasts, throw debris into the atmosphere. How does that scale of event play out? How local is its damage? How long do its fingerprints linger in ice, in sediments, in ecosystems? If we can recognize a pattern, if this is what a subcontinent-scale airburst looks like in the geological record, then we're not just solving a mystery, we're building a template, a way to estimate what might happen if something similar occurred tomorrow. How many people would be affected? Which food systems would be most vulnerable? How would climate respond? Those are not abstract questions. Modern surveys of near-Earth objects show that city-killing and region-killing bodies do exist, and they do cross our orbit. Studying ancient impacts, real or suspected, is part of learning how to see these hazards in time, how to track them, and if necessary, how to divert or break them up before they turn into another abrupt chapter in Earth's story. But the Younger Dryas also teaches us something subtler about resilience and fragility. On one hand, the planet recovered, ice retreated, forests regrew, new ecosystems emerged full of new combinations of species. Humans didn't die out. On the contrary, within a few thousand years of the Younger Dryas ending, people were inventing agriculture in multiple parts of the world, building permanent settlements, laying the foundations of everything we now call civilization. On the other hand, recovery didn't mean restoration. Many megafauna never returned. Entire ecological roles, giant browsers, giant predators, giant diggers and tramplers, vanished in certain regions and were never refilled. For tens of thousands of years since, those missing pieces have quietly reshaped how ecosystems function. Fire regimes, plant communities, nutrient cycles, all still bear the marks of that extinction wave. That's what deep history shows us. Earth as a system is robust. Life adapts, fills gaps, finds new strategies. But individual species, and even whole ecological structures, can be shockingly fragile. Once gone, they don't just pop back into place when conditions improve. The system moves on without them. So when we ask how vulnerable modern ecosystems are to sudden shocks, the Younger Dryas whispers an answer. Very. Especially when they're already stressed. Especially when multiple pressures line up. Climate, habitat loss, overuse, invasive species, and then something abrupt nudges the system one step too far. The good news is that we, unlike the people staring up at the Younger Dryas sky, know that these processes exist. We have ice cores, sediment cores, computer models, telescopes tracking near-Earth objects. We can see some of the hammers coming. The question is whether we treat deep history as a distant curiosity or as a manual, a record of how our planet behaves when pushed, of what breaks, of what survives, and of how narrow the passage can be between disaster and renewal. So where does all of this leave you, lying in the dark, listening to stories about a cold snap 12,800 years ago and a sky that may or may not have been on fire? On one side of the scale, you have the impact hypothesis, a dramatic story, fragments of a shattered comet slamming into ice sheets, forests and oceans, firestorms racing across continents, black rain, sudden floods, walls of meltwater tearing through valleys, a single night, or a handful of nights, that tilt the climate into chaos and push mammoths, mastodons and giant ground sloths toward oblivion. On the other side, you have the slow, relentless machinery of Earth's own rhythms, subtle wobbles in the planet's orbit, shifts in ocean currents, freshwater pulses shutting down the great conveyor belt of the North Atlantic. No fireworks, no blazing sky, just physics, ice, and time quietly conspiring to flip the climate from warming back to deep cold. Cosmic collision or natural climate shift, a sudden wound or a sharp turn in an already winding road. That's the heart of the Younger Dryas mystery. We do know some things. We know the cooling was real, abrupt, and global in its reach. We know that megafauna vanished in staggering numbers, that human cultures were forced to adapt, relocate, or disappear. We know there are strange layers in the ground from this period, full of clues, microspherules, soot, platinum anomalies, broken tools, abandoned camps. But we also know that evidence is messy, that some sites show one pattern and others show something different, that dating techniques have margins of error, that geological processes can mimic the fingerprints of catastrophe, and that smart, careful scientists can look at the same data and arrive at different conclusions. What sits in between is the space this channel lives in, not blind belief in the most dramatic story, not rigid dismissal of any idea that doesn't fit the neatest model. Instead, a kind of disciplined curiosity, a willingness to say, here's what the evidence shows, here's where it's strong, here's where it's thin, here's what might be true, and here's what we just don't know yet. This question keeps pulling people back for a reason. It speaks to something deep in us, the sense that history isn't just a straight line, that our world has been shaped by rare, violent moments as much as by slow, patient change. It touches our fear of sudden disaster and our fascination with it. It asks whether our ancestors looked up one night and saw the sky burning, whether they told stories about it around fires that eventually became myths of dragons, serpents, and angry gods. It also reminds us that we're part of a much larger pattern. Comets still cross Earth's orbit, ocean currents still shift, ice still melts and grows. We're not outside the system, we're inside it, just like the people who watch the Younger Dryas unfold. As you drift towards sleep, you don't have to pick a final answer. You can hold both possibilities at once. A planet capable of staggering climatic mood swings all on its own, and a cosmos where, from time to time, a piece of ancient ice and rock falls out of the sky and changes everything. That balance between certainty and mystery is where the most interesting thinking happens. It's where science lives at its best, testing bold ideas, discarding some, refining others, always moving, never quite finished. If you enjoy exploring that edge with me, staying curious without needing all the answers, I'd love for you to be part of this little community we're building here. Gently tap like if this helped you relax or gave you something to think about. Subscribe if you'd like more journeys into deep history to fall asleep to. And in the comments, if you feel like sharing, tell me where in the world you're listening from and what time of day it is for you right now. Midnight in a city apartment, early morning on a farm, late afternoon with headphones on a bus. Those tiny details turn this from just a video into a circle of people scattered across the planet, all drifting together through the same ancient stories. For now, let the questions rest. The evidence will still be there in the morning. The mystery will too.